So now before we get too far into qubits, let's talk a little bit about a primary kind of physical concept behind the operation, the functioning of qubits as a whole. And that concept is superposition. This is essentially what makes it possible for a quantum computer to represent several states at once. So you may have heard of this term before, perhaps from the classical physics perspective. In classical physics, this essentially refers to the interaction, say, between two physical materials or quantities of some sort to result in a third physical quantity that has slightly different characteristics. So if we were to look at it from the perspective of, say, waves, you might have two waves that are in phase with one another, and through what is known as constructive interference. Constructive interference. Right? Constructive interference. We end up having a wave that results that has a slightly larger amplitude from before. You have two physical quantities that interact to create a third physical quantity. And of course, if you have, say, constructive interference, we quite naturally also have what is known as destructive interference. And this occurs when your waves are out of phase with one another. Just to clarify, destructive interference. Right? And so when your waves are out of phase with one another, they happen to cancel out, and you end up with, say, a straight line of some sort. Again, a third physical quantity with slightly different characteristics. If we talk about superposition in terms of forces, again, still in classical physics, right, you might have a force that is acting on an object in some given direction, some given magnitude, and you have another force also acting in the object, and the net force that results will be some superposition of these two vectors that we have right here. Now, if we were to look at, say, quantum physics and superposition from the quantum mechanics perspective, there are several things that we do need to note. First of all, quantum mechanics looks at things on the tiny little mini scale, right? Quantum. And this is smaller than, say, your teacup pig. This is smaller than the head of a needle. When we look at things from the quantum perspective, we're talking about particles so small that even the mere act of observation can change their state, right? So when we talk about quantum and quantum level things, there are several things and observations that need to be made. First of all, there's the idea that energy is quantized. And when we talk about energy being quantized, this was not technically first proposed by Max Planck, but most famously proposed by Max Planck. Perhaps I think Newton did touch on something, a concept that's slightly similar before. But anyway, what Max Planck essentially said was that energy comes in these little packets, right? And energy coming in these little packets, these are very small. And what quantized energy and what energy coming in packets basically means is that the amount of energy that a given object, any sort, any particle has, can be expressed as an integer value, and it cannot be expressed as anything in between, meaning that you can have 0, 1, 2, 3 units of some energy, right? But you can't have 0.5 units of that energy. You can have 3.2 units of that energy, right? It has to be expressed as the integer value of some sort. Now, going on from there, why don't we see this, say, on the macro perspective? Why don't we consider energy being quantized when we throw a ball in the air? And the reason being that when we look at things from the classical perspective, right, we're considering so many particles, and we're considering a huge, huge number, right? We're talking about this many particles, right? All these different kind of particles, they're all there. We're all, observing them all at once, such that there are so many that we can actually, in fact, consider it to be seen as, say, a block of some sort, right? Because there are so many particles, this is what we end up observing. Now, when we look at things from the quantum physics perspective, however, things are slightly different, right? Quantum, maybe make that a little bit neater. Quantum. Right? Things are so small that we're observing a few particles at once, and as a result, consequently, when we talk about a few particles at once, it becomes quite clear that this energy of these particles is indeed quantized, and so as a result, the observations that we make are slightly different. Now, going back to the idea of energy being quantized and looking at things from the quantum level, when we say have a given particle, there are several things and several observations additionally that can also be made. So one of them being the idea that, let's say we have some coin. And we throw in the air. It has some probability of landing either heads or tails, and we know typically that's approximately 50-50, right? So if we have, say, like a particle or some coin has heads. And as soon as we look at this coin after we flipped it and we see that it's landed on heads, we have the definite state of that coin. It is known. We know that it is at and it has heads. It has landed heads up. And this state just basically means that we're talking about the way the system can be described. And so this state is in fact related to these quantized values, these quantized energy values that we described before. If we were to talk about, say, an electron orbiting a hydrogen atom, in this case, and the hydrogen atom, you may or may not be familiar with this, was in fact studied by this guy named Bohr, right, Niels Bohr. And what he did was he modeled the hydrogen atom. He successfully did so by quantizing the energy levels of this electron that goes around the given hydrogen atom. So if we talk about a hydrogen atom, right, it has atomic number 1, and ideally, if we have a hydrogen atom, right, we've got one little particle guy kind of going around. This is definitely not to scale, right? We have this little guy running around kind of in the orbital electron cloud around your hydrogen atom. What Niels Bohr was able to do was that he was able to show that this electron could either be in the ground state or the excited state. And those are the only two states that it could essentially be in. Now, a quantum system essentially looks at some given particle or these given particles or these just particles in general, and it says it can be in the superposition of these definite states, right? So what that means is it's like saying in the context of a coin, it can be both heads and tails simultaneously, or your electron can be in both ground state and its excited state simultaneously with some given probability. And so to illustrate that, Schrödinger, rather well-known physicist, for his thought experiment came up with what was known as Schrodinger's cat. Now, Schrodinger's cat involves this lovely little cat here, right? And this cat here is put in a box. And this box is closed off from the outside world. And what that means is that no light can get in, no observer can get in, nothing can get in. The cat is in this isolated system, and let's say we put some radioactive, deathly radioactive particles in with the cat. And I've denoted that with this little green box right over here. Now, radioactive, radiation emitted by some given set of particles that have that kind of nuclear potential energy here, that have the potential to break down. The radiation that is emitted, definitely it's there, and let's say it's deadly. So the moment a single particle releases that radiation, this cat is dead. Now, here's the thing though. We are aware that the act of nuclear decay, which releases your radiation, is indeed a spontaneous process. However, with it being spontaneous, it's actually impossible to predict for certain whenever this given nucleus, this set of particles will actually decay. And so, of course, we do have some probability. We know that maybe after some given set of years, the half-life of your particles have passed. And perhaps, from a probability perspective, there's a higher chance that around half of your particles have decayed. But here's the thing. The key word here is, we think, probability. Kind of, maybe, sort of. Because there is also always a chance that none of these particles have indeed decayed, because again, it is a spontaneous process. And so as a result, before anyone looks into that box, before anyone can even observe the cat, it can be said that the cat is both alive and dead with some probability. Naturally, as time goes on, that probability of it being alive does decrease, but we can still nevertheless express it as some probability of the cat being alive and dead. And so, in other words, just relating it back to what we've been talking about this entire video, the cat is in some quantum superposition state until we open that box, until we measure it. And the moment we look at that cat, the moment we measure its state, the superposition essentially collapses, and we have a definite state for the cat. A definite non-superposition state. I apologize. Of course, this is slightly different from our classical point of view, from the classical physics perspective. But naturally, we don't see quantum superposition in macroscopic objects, so it's perfectly normal to be a little bit hesitant to accept this and to kind of look at things from this perspective. Nevertheless, again, quantum superposition is what allows us to have these quantum computers that exist in several states at once for their given qubits, have these qubits existing in several states at once. So this basically summarizes and gives a brief look, a conceptual look at superposition as a whole, touching both on the physical, classical physics side and perspective of it, as well as the quantum physics, quantum perspective of superposition. And as always, if you have any more questions, feel free to visit the Q-munity Tech website. And as always, stay curious and keep on learning.